Hey everyone, I'm just opening the stream in a separate window so that I can be sure that is happening. And in case something like what happened yesterday happens, when I was talking about embeddings for the whole hour, and then I found out that actually there is nothing showing on my screen because of some glitch. So yeah, I have removed this video and I will not talk about embeddings for some time. So I will just be controlling this on the side screen here. But yeah, nice to meet you all, and thanks for joining me today if you joined. Let's solve another hard problem. And this problem is binary tree cameras. I have never solved it before. Let's see. You're given a root of a binary tree. So root will be something like tree, probably optional. So optional tree, no, possibly none. We install cameras on the three nodes, where each camera at a node can monitor its parent, itself, and its immediate children. Return the minimum number of cameras needed to monitor all nodes of the tree. Okay. Interesting. Okay, at least I know that we will be returning integers. Let's do some tests. So let's say we have a tree, like, okay, it's a binary tree, so it doesn't have to be binary search tree. Can we just assume that the nodes are unique in case we need to store something for the nodes? So no, the number of nodes is in the range to 1000, but for all nodes the value is 0. Okay, so I will not make it 0, I will make it different numbers, but this is just needed to reason about the problem. Okay, so 4, 5, and let's say 6. Okay, so what would be the minimum number of cameras needed to monitor all nodes of this tree? I think it's 2, but is it? So we need to monitor these leaves, then we definitely need to monitor these leaves. So if we start at the leaves, then we have to either have a camera at the leaf or at the parent level. Okay, so when do we need to have camera at the leaf level? When another camera is like 2 levels above. So this camera will be tracking these 2 nodes, but this camera, there we don't have camera, so we'll have to install camera here and camera here. So essentially, I'm thinking about 2 directions, right? Like top down and bottom up. Top down is easier to conceptualize because in this way we have children, but if we do bottom up, we kind of have to consider both questions, but I mean both questions, whether to install camera on a node or not, but we don't have pointers to children. So I will mention some challenges that I see here. So challenges are that no greedy approach. So it might be that because of this structure where we have some nodes don't have other nodes, let's say we also have 7 here, right? So because of that, we cannot just make some algorithm that says, okay, just put the camera here. If we put the camera at the root, then we need to put, don't need to put cameras here probably, but then we would need to put the camera either here or here. But then because this camera is covered. But even though this camera is covered, instead of putting cameras both at 4 and 5, we can just put camera at 2. And then we will cover both 1 and 2, but there will be overlap between cameras because 2 will be observed both from camera on 2 and camera on 1. So there is like this pattern where we don't really know what's the minimum amount of cameras that we need to install. But okay, what I'm thinking about the solution is we can do dynamic programming. I will get to the to my explanation there, but why do I think that there is no greedy approach? That's one challenge, but another challenge is that on average, not on average, at most, like the brute force solution would be to decide whether to install and not install camera on each of the nodes. So it will be if we have n length of nodes, total number of nodes, right? Then it will be O of 2 to the power of n brute force, which with 1000 nodes doesn't work at all. So now how do we go about this? What is my dynamic programming idea that I have? So I see the recursive relationship that can be solved with memorization. So the problem is, like, let's say we install camera on 1, right? Then we have several options to go about this node. So what if we install camera? What if we don't install camera? What if we install? What if we don't install? Then let's say we don't install camera here. Then there is also like, what if we install camera here? What if we don't? And the same thing here. So we are again and again solving this problem for like what would happen if we install camera at this point. What will happen? What is the minimum number of cameras needed to monitor all the nodes starting at this element as the root? That's the recursive solution that I see, right? Because basically at each node, we will need to figure out like what is the direction that we need to go. And then if we calculate options just once, so if we memorize, right, like how many cameras do we need to install if we install camera at this node, and otherwise if we don't install camera on this node, if we are assuming that we are not there is no parent at all, right? So we have this root here. So assuming that we don't have any parent, what is the minimum number of cameras needed to monitor? Then let's say we are at this node and we need to decide. We will know 3 things. Like if we install camera here, we don't need to install camera here, and we don't need to install camera here, but we might. So it's like we choose minimum out of what happens if we install and what happens if we don't. And here we choose minimum, what happens if we install, what happens if we don't. But then if we don't install camera here, we are forced to either install camera here or here. If we do install camera here, we are not limited to either installing here or here, and we can consider all the possible choices. So then we can calculate this in like of one time if all of these other options are already memorized. So if we continue doing this down the line, for each node, we need to do just a constant amount of operations in total. And that would bring us, would it bring us to linear time? I don't believe that. There are just too few nodes for us to be able to get to a linear decision. So let me tentatively say that it looks like it will be all fun because we are just solving this recursion once. It's like as if we were doing Fibonacci in a way, right? We memorize things and we just need, for each element of Fibonacci sequence, we need to calculate things just once. And then on each step, there is a very limited number of options that we need to consider. The thing that I'm worried about is like, why then we have just 1,000 nodes? It sounds like the solution should be like at most 10 log n in this time, and I'm figuring out a linear solution. So yeah, maybe there is also like in terms of memorization, we will need to store for each node, we will need to store two numbers. One if we install camera at this node, and one if we don't install. So it will be also often in space. So given that I don't have any other ideas about the problem, I will just assume that this is the correct running time, and I will get back to it once I solve the problem and see if I'm wrong about this. Maybe I'm missing something. Okay, so min camera cover. If root is none, return 0. So we need 0 cameras to cover a particular node if it's not a node. That was easy. Now let's try to think what we need to do, what are the options that we need to consider. Then, okay, so if we install, okay, how do I store? I was thinking about how should I create this recursive function that stores information. But the problem is, right, if we had all our trees, like all of the values would have been unique, we could have just used values as a dictionary key and memorized this way. But now that we cannot do that, it looks like maybe there is the problem is this, right, that we have to create, like we cannot just memorize. So we have to create some structure for memorization. So then we will probably need to create a sub-function where we're not only passing the root, but we are also passing like not only passing the node, we are also passing whether we have to use this node and don't have to use this node to cover all possible variants. Okay, so define method for min cover for node, and here we will be using self, and will be node, which is optional of tree node, and then needs cover, which is boolean, and it can be like, do we have to cover this node? And then we have an integer here. Okay, so if node is none, return 0. Else, what do we do if node is not none? So if needs cover, then we need to return minimum of self min cover for node. Okay, here we still cannot. How do we store this in cache? Is this the main problem here? The main issue of this task? Like, how do we store it? So if it was just value, all values weren't 0, then it would have been easier. But here we will have to figure out how to uniquely identify the node. And there are several possible ways to uniquely identify the nodes. I'm just figuring out like what would be the easiest and cheapest way. So let's have memory. Let's call it self memory. And it will be a quality dictionary. So how do we store information in memory? Right now we don't have the node. So we have node IDs, which will be stable across this problem. Should we just use ID in Python, like object ID as our hash? We can use that. Okay, I think it should work, so why not? If we couldn't use an ID, we would need to figure out like we have a parent, and then we can just can call the parent P, and then we pass a sequence of characters. Like for example, we have current node as sequence of characters, and then we pass to the child that the child is remembered as like this sequence plus right child will be R and left child will be L, and then the sequence will uniquely identify all our nodes, and we have at most of n length of the string. The problem here would be that adding characters to the string will be of an operation or of an operation, and then that would increase our runtime for this algorithm. So how do we quickly do that? I don't know how can we quickly hash our particular node in a particular place in our tree. Yeah, I think it can be some integer manipulation. So we can just multiply by some value each time when we are going one level below. Oh yeah, we can have a binary sequence. Yeah, I think we can have a binary sequence, and that would be more clever. Okay, so let's then not use object ID because this will be Python specific, and I'm not even sure that would work, to be honest. So let's instead have parent, which will be an integer. Okay. So current node will be equal to parent, moving all the binary elements by one, and no, we will node ID. We will be doing it here. We will be calculating it for left and right child. So we don't want to pass information here, whether it's the left child or the right child. We will instead calculate it here. So okay, needs cover. What do we return? So first of all, let's calculate. If needs cover, then we can either cover the left node or the right node. Use camera either on the left or on the right, because we are on the current node, on the left node, or on the right node. Okay, so cover current node means we will have like one camera plus self min cover for node. And now what do we do? Let's here calculate indices for node IDs for the left and right child. Left child ID will be equal to node ID times 1, and like the left child will be 0 and the right child will be 1. So right child ID will be this or 1. Yeah, so we are here the last bit will be 0, here the last bit will be 1, and all the other bits will be moved by 1. So now we have left child ID and right child ID, and then if we cover the current node, cell cover for node will be okay, left child ID and node left, and needs cover false. If we are covering the current node, it doesn't need the cover. Plus yeah, I probably should make this calculation look nicer. We are too far. Okay, plus, and here we will also be adding self min cover for node right child ID and node right, and we still don't need the cover. So we covered the current node, we will get this amount. Then if we then we can also cover node cover left child will be just this, but here we will also be changing. So if we cover left child, we require that, oh, let's specify what does it mean that it needs cover. Let's call it needs camera, because if needs camera, then we don't need to do that. We will just, we know that it doesn't, okay, if it needs camera. Yeah, there is the problem, right? It can either need camera or it might need cover. So can I define it in both ways, or is it just one of those that will work? So let's say it needs camera. Let's say use camera. So if we cover the current node with a camera, then okay, here we would need to choose minimum of this, and because as we have seen here, it doesn't have to be true that if we use camera here, we don't need to use camera here. So if use camera, yeah, if use camera, we need to to calculate it both for the left and right child. So left child cameras will be equal to this minimum of this and this. Okay. Right child cameras will be equal to minimum of right. So if use camera, we are definitely true deploying camera on our parent, so we don't have to use cameras on our child. So we need to figure out what's the minimum amount of cameras that we can get if we use camera for the left child or if we use camera for the right child. Now else, so here we don't use the camera, but how do we pass information whether we, so we are not using the camera. So use the problem I see here is if we just interact with children nodes, what does it mean that we don't use the camera? So let's say we are forcing that we don't use a camera. Does it mean that we are covering it ourselves? No. Oh, yes, it does mean that, right? So here it will be return 1 plus right child cameras. So here we are ensuring that we have camera on our parent, so our children don't have to have cameras. And they can choose either to have those or not. So if we are not requiring to use a camera, then we can assume that how many cameras will it take? So we don't need camera for this element right now. But how do we also track that? Let's say we install camera on one of our children and then it will cover us, right? So let's instead use a different function yet again. Parent provides cover. So let's say parent provides cover. If parent provides cover, then we don't need to have a camera. So here, if not parent provides cover, what does it mean? We need to either install camera on our left child or our right child, or for ourselves. So if not parent provides cover, then we will need to install on node. Then the amount of cameras will be install camera on node. We provide children with cameras, so then this will be camera on node will be equal to left child cameras plus right child cameras plus 1. So this means that we install camera on this node because parent doesn't provide the cover. But then there is also like another option Oh, I see. So instead of, we also need to be able to require a specific node to install camera, right? Like a specific child to install camera. So if our parent doesn't provide cover, then we need to also use camera boolean. Maybe there is a more elegant solution that I just not seeing. Install camera on left child. So if parent doesn't provide camera cover, then we need to install camera on left child. Then it means that, okay, here we need to check even more things. So parent provides cover. Here, actually true, parent provides cover. So we are providing cover and we don't require this node to install camera. And parent provides cover and we do have to install camera. This is too inelegant. There definitely is a simpler solution. So what if parent provides cover? So for any specific node, the cover can be provided in three ways. Either it's provided for the parent, or it's provided from the child. So then to decide, or it's provided from the node itself. So when we are installing camera here, we need to decide whether we want to install camera here, and then children can do whatever they want, or we have installed camera on the parent. So if parent provides cover, then it has to mean that we have installed camera on the parent, right? So if we have installed camera here, then it means that we can choose whether to install camera or not. But the parent, for the whole thing to be valid, parent also need, if parent doesn't provide cover, it doesn't mean that parent has or has no cover. Parent provides cover. Okay, parent has cover. I think this is cleaning things up the easiest to reason about. So let's say that we have here, right? We also need information to this node, whether parent has cover and but parent has cover, no, then children nodes will not know if they have to install camera. Parent requires cover. Okay. Yeah, so I think this covers it all. So then if not parent provides cover, we need to either install camera on node or install camera on the left child, or install camera on the right child. On right child. Then else here, that would mean that parent provides cover, then we can choose whether we can decide whether we want to install camera, and then we will say that install on node, or not install and not require to install. Install a node and provide cover, or not install and not required to install. Okay, so if not parent provides cover, let's actually do it. I will just create a new thing here. So if parent requires cover, else. And then if parent requires cover, okay, the thing is that parent cannot require and provide cover at the same time. So if parent requires cover, then it definitely doesn't provide it. Else, if parent provides cover, then it's, if parent doesn't require cover. If parent provides cover, that's one thing. And then else, parent doesn't provide cover. So this will be a three-way conditionals. Okay, if yeah, I think I will just, we can obviously like combine those things, but for example, if not parent requires cover and parent requires, if, okay, sorry, and parent provides cover. Okay, so we can do if not parent requires cover and parent provides cover, and then else, but else if, but I don't want to do that. I think it's more straightforward to do it this way. So okay, if parent requires cover, then we have to install camera right now. So we are installing camera on node, and then we cameras equal 1. Then left child is provided with cover, and obviously then parent doesn't require cover. So then min left, or let's continue with left child cameras, will be minimum of self this. Okay, so what are we doing here? So left child cameras, self cover for node, left child ID, node left, and now left child is provided with cover, parent provides cover, true, parent requires cover, false, right? Okay, this is good. So if parent provides cover true, parent requires left child cameras, so we don't need min here. Right child cameras will be the same thing, but node right. So if parent requires cover, we definitely have to install camera on the node, and then we are making it more lenient for our children. They will be able to be more flexible. So here we return cameras, or maybe let's return 1 plus left child cameras plus right child cameras. Okay. Okay, so here we just return this. I'm also not making the memorization part yet. So that's another thing. Okay, if parent provides cover, that means parent requires cover. If parent provides cover, then here we will actually have options. So parent provides cover, then we can decide whether we want to install camera on this node or not. So then install on node, and then cameras will be the same. And here. So if we are installing, parent provides cover, we can still install camera on the node. And +1, so okay, so here that's one. Then install don't provide cover. So parent doesn't require cover, but parent doesn't also provide cover. So here we will see not install node will be so here we will have left child cameras, left child ID node left. So does the parent provide cover? False. Does the parent require cover? Also false. And here right child cameras, left child cameras. So we are not installing, we just do that plus that. Okay. So parent provides cover, but or don't provide cover, and then here we are returning minimum of install on node and not install on node. Okay, sounds good. So now else here the parent doesn't require cover. Oh, here parent doesn't require cover, but we are not installing camera on our node right now, so we have to enforce one of our children to install the camera. So install on left and install on right. So if we are installing on left, then left child cameras will be node left true. Okay, so what do we have here? Parent provides cover, false. Parent require cover, finally this is true. We do require cover. Left child cameras. And right child cameras will be. So if we installing camera on the left, then we can leave our right child be and don't need to require camera there. Install on right, sorry, on left will be equal to plus right child covers. Okay. Then install and write will be the same thing, but we are not installing on the left child, but we do require installing on the right child. And then install and write will be again that. So in here we return minimum of install on left and install on right. Okay, so this part we can leave out of consideration. Yeah, that was incredibly tricky. So now the only problem is, how do we figure out what do we need to return here? So memorization, right? So we just need to do if node ID and parent provides cover and parent requires cover in self memory, return self memory, and here we will pass this index. Okay, else we need to do everything here. So here we are not actually returning. Answer will be this, or answer will be this, or answer will be this. And once we have recorded we have created our answer, we'll be first updating self memory for this specific node ID with this specific parameters will be answer, and then we will be returning answer. So now we have memorization. And finally, we just need to do self min cover for node, and node ID will be just, let's say 1. We will start with 1. We could have started with 0. So min cover for node 1, where we have node as root, and parent provides cover false. It doesn't provide cover, but it also doesn't require cover because we don't have a parent. So answer will be this, or maybe we should just return this. Okay, this is it. Now let's go back to our space and runtime calculations, right? So what's the problem here? The problem here is that we have calculations. We are calling this function min cover for node up to 4 times on each of the iterations for each of the nodes. So if we are recursively calling this function 4 times, then it can grow exponentially, obviously. So yeah, on each iteration, we are calling it 4 times. And on each call, we are doing just of 1 amount of operations. I remember there is a rule on how do you, and okay, you also need to figure out how much fewer work you need to do on each call. Okay, that was for divide and conquer. So here, let's see, we have 3 nodes, right? So this node, okay, this node would require 4 calls to the function, each of those 4 calls will go here, and this node will also require 4 calls. But there will be this node will just receive 2 different probability. No, it won't receive. It will receive 4 options. Yeah, so it basically like 4 to the power of however deep our tree can go. But is it though? So for example, let's say we have this line right here. We do 1 call on each layer. So let's say it's a very, very deep tree. That is unbalanced. So here we will have it's not working well, right? Because right now we are returning, if we there is another issue with this solution right now, that we are still considering, like, we are returning 0, but that's incorrect. Like, let's say we came from a parent and we can only require parents or children to install cameras if these children exist. Right now we are coming to those children and checking. So okay, so install a node. If we are installing a node, then we are fine, right? Installing camera on node, we don't need to worry about this child or this child. So parent provides cover, doesn't have to install. It will just return zeros. Okay, so then if parent provides cover, then again here for children, if parent provides cover, we don't have to install camera anywhere. But here, install on left, we have to okay. So what if we go to a child, parent doesn't provide cover, we cannot not provide cover. Here, parent doesn't provide cover, and parent requires cover. Here we actually have forgotten about the base instance. So if parent doesn't require cover, and parent does not provide cover. Oh, if okay, parent requires cover, we have to install camera, but we can only require cover we can only require cover from children that exist. So here we're explicitly parent doesn't require cover, so parent is covered. Then we can choose either to install or not install. And then if parent doesn't provide cover, then we have to either install here or on the children. So here we also have to install a node. Okay. Let me simplify all the calculations. Oops. So install a node. Oops. Okay, install a node. This is what we are getting forever if we provide cover and doesn't require cover. Okay, so then here we can remove that and just say that the answer is install a node. Here we don't have to recalculate installation on node, so we can decide not to install a node and answer minimum of install a node and not install a node. Okay, that's reasonable. Else we can have install a node, that's the default value, and then we only have options of not installing a node. If we have children. So install on left float of infinity. So this is install on right by default is also right. Install on left is float on infinity. So if node left is not none, we are updating install on left. And here, if node right is not done, then we are updating this on the right, install on right. Answer here will be minimum of install on node, install on right, and install on left, because we here we can choose whether we want to install or not want to install camera on this specific node. And if we are installing, we are providing cover, otherwise we are not providing cover, and we also require cover. Then this is crazy. I have already spent too much time here. I should have spent it on something better. Okay, it works. Wow. Damn, it works on the first try. Wonderful. I'm happy. After all this suffering. But it's not an optimal solution. And let's also, like we were discussing, the running time of this algorithm. So on each layer of our tree, we are making 4 times more recursive calls. So with each layer, we are doing 4 recursive calls, but each of those recursive calls, once it's stored, it will be all of one operation, right? So here we need to calculate it 4 different ways. Here we need to calculate it 4 different ways. Here we need to calculate this result 4 different ways. And since we are calculating it all just once, I think this is still correct. But yeah, I digress. I'm tired. 1 hour spent here. Don't want to spend any more time. Thank you everyone for watching this, and see you later. Bye.